All right, so we're back. It's my pleasure to introduce Max Kuhn, who's going to be talking about ensembles using tiny models. Go ahead, Max.
Great, thanks for having me. Turn my timer on. Okay, so I want to talk about a method for creating ensemble models using the tidymodels infrastructure. This is work with Simon. It was his summer internship this last year. So to be honest, he did most of the work here. So we normally think of ensemble models with things like random forest or boosted trees, and those work really well. One thing to note about them is they are ensemble models that have different individual models embedded inside them that are all the same type. So for example, a random forest model consists of hundreds or thousands of individual cart or tree-based models inside of it. So we normally think about the ensemble models that we hear about for the most part. Those are ensembles of the same type of model. But it turns out that the person who invented ensembling, at least in the statistical literature, his original shot at that was called model stacking. And that was a way to take disparate types of models. So let's say like a neural network and a linear regression and different types of models and blend them together in an ensemble in an effort to hopefully get better performance. And so model stacking is what we're going to mostly talk about in this particular presentation. On the right-hand side here, we have a little bar chart from a presentation. On Twitter, we did like a user and developer survey and gave them a menu of things that they could basically put like hypothetical money down on in terms of helping to influence our development. And kind of surprisingly, model stacking, almost every way we cut it, seemed to be one of the most requested features for tidy models. So that's what Simon spent his time on. He created an R package called Stacks, and that's what we'll mostly talk about today. So to sort of illustrate how Stacks works, let's just go through the individual steps of how you would create like a stacking ensemble of models. So the first thing of interest is you define the models that you would like to include in the ensemble. And so, normally when I used to do a lot of modeling in pharma, we would do a lot of different types of models to see what we could predict. And at the end of all that, we would take the results that we had developed so far and try to put that into an ensemble to see if that would make it better. So basically the first step in defining the ensemble is to come up with the models that you would like to be inside the ensemble. And so, for example, if we did like a k-nearest neighbors model, linear regression or neural network, we might look at those three as being potential members of the ensemble. So the first step is defining them. So with the linear regression model, if it's like ordinary least squares, it's not really all that complicated of a model. But for things like neural networks and other models, we have these things called tuning parameters. And tuning parameters are different configurations of that particular model. They're like submodels that we might test to see which one works better. So if we're looking at a k-nearest neighbor model, the tuning parameter would be the number of neighbors. So we might try a 1 nearest neighbor model or a 5 or a 10 nearest neighbor model. And so sometimes when we define the models, we have to define like what structural model we want to use, as well as like what submodels we want to evaluate. So how would we do that with tidy models? So if you've never used it, we have a book and a few websites that you could look at. Here's a link, goes to a GitHub site that has all the details from the models that we looked at. I'm going to load some initial tidy models packages, including the new one called Stacks. The example here comes preloaded. It's a high content screening oncology assay problem. It's a pretty interesting example. Basically, the data in there are measurements of different cells with a classification outcome. And so what I'll do is I'll initially make a training and test split of that data. So I'm putting about 3/4 of the data into the training set and 1/4 into the testing set. And so once I have my training set set up, we can start to define what models we'd like to look at. And so I'm going to use about 6 or 7 models in this presentation. I'm just going to show you how in tidy models you would specify those. So a good example would be a random forest. So if you wanted to define a random forest model, you would use the parsnip random forest function. And then you could say what parameters you want to specify or potentially tune. So if we want to tune mtry, or the minimum number of data points needed to create a split, we would give them a value of tune, and that sets a stage for them to be optimized in some of our other software. This naive Bayes model that's defined here basically does some initial pre-processing using a method called recipes, and that will sort of transform our predictors to be in a little better distribution, like less pathological distribution than they are originally. And then we can fit the naive Bayes model and optimize the smoothness of the non-parametric kernel density estimator. So these two models are interesting in the fact that they have different submodels that we'll try. And then we go to tune these models, which will get used inside of the ensemble. We can specify, for example, how many combinations of these particular tuning parameters that we want to evaluate. So once we've defined our models and submodels, the way we would typically tune is using something like grid search. And in grid search, you define a resampling method like the bootstrap or cross-validation. And using the resampling method, you would evaluate all of your potential submodels you might have with each resample. And then for, let's say, the k-nearest neighbor model with one neighbor or four neighbors, you would evaluate them using resampling and get a performance measure like, area of the RC curve or accuracy. And then you can choose the appropriate, if you wanted to finalize the model, you could choose the appropriate number of neighbors based on the resampling performance statistics. So the cool thing about stacking is it uses our resampling results in the course of generating the ensemble. So we'd have to do some sort of resampling or, let's say, a validation set to be able to produce the stacking model. So let's resample the data. It's pretty easy to do in tidymodels. We'll start off with a little bit of specifications. We save the out-of-sample predictions and a few other things. We can set up a tenfold cross-validation very simply just by defining an RSample object using the vfold CV function. And then let's say to tune the ranger model, we give it the specification we had before, tell it what the outcome is and what predictors to use. And then what we'll do is we'll come up with what's called a space filling design of 25 different possible values of m-try and min-n, and it will resample each of those 25 values. So we have tenfold cross-validation and 25 specifications. This code would basically fit 250 different models. Similarly, for the naive Bayes model, we have 10 different values of the kernel smoothness parameter that we'd evaluate across the 10 different resamples. And so these tune objects that come back basically contain all the information about performance as well as the out-of-sample predictions for these models and the submodels that were evaluated. So the results, we have a bunch of accessor functions if you want to look at the results. For example, if you want to look at what the actual performance statistics would be, you can run the collect metrics function on one of these objects and see, you can get the averages, but in this case, I'm showing that for m-try of 27 and min-n of 5, for fold 1, the area of the RC curve was about 90% and so on. Now, perhaps more importantly, what we use with the stacking ensemble is we'll use this collect predictions method under the hood, and that will give us the holdout predictions across all the submodels. So for example, for this particular random forest submodel that we used, the original row 1 in the training set, when it was held out from the model and then repredicted, we had these predicted class probabilities and so on. So this is the important part that we need for the stacking model, is we need the data points that were predicted when they were not part of the modeling process. So those are our out-of-sample predictions. And for these results, across the models that we fit that you see here, and the results are they're not bad. One model, naive Bayes, didn't do as well as the others, and most of them are hitting sort of a ceiling on performance at about somewhere between an RC curve score of 0.89 or 0.91. So they sort of hit a ceiling on prediction for this particular data set. And you can see also how many submodels that we evaluated when tuning the model. For something like naive Bayes, 10 would be good. For C5 or some of the other more complex models, we attempt more submodels because they need a little bit more tuning than others. So you can see the number of submodels is really up to you, and they might vary across different modeling functions depending on how many tuning parameters or just your interest in the model would be. So what we'll do is, you'll see in a minute, is we can take all these submodels and enter them as possible candidates for the modeling ensemble. So now that we've resampled our models, we've specified what we want, we've resampled them, The next thing we'll do is we'll actually create what we call the data stack. And it takes all those out-of-sample predictions that I showed you a few minutes ago across all the different models and submodels and just collates them, right? So it takes, sample one for this submodel for K and N and matches it up to the same out-of-sample prediction for the second K and N model and so on. So it just lines up all the out-of-sample predictions. So to do that, you would create, using the stacks package, a new data stack using the stacks function. And then you just pipe in which models that you potentially want to add. So these are all the tuning results for the different models that we had. So for example, here's a naive Bayes model and the Ranger model that we looked at. And basically this just, makes sure that they were all used the same resampling indicators and have the same metrics and things like that, and just gets all the data together in like one big tibble. So a big data frame. And when you print that out, it basically gives you a list that there were 6 models that were used and 322 candidate members, meaning across those 6 models, this is the total number of submodels that were evaluated. And it gives you the breakdown of each here. It also tells you that you're trying to predict an outcome. So one thing about the data stack here is it takes the original outcome from the training set and matches it up to all the out-of-sample predictions. So for example, since we have 2 classes here, this column in the data stack for the first K-nearest-neighbor model will be, let's say, the class probability of the first class in the outcome. So in the case of a classification, these would be class probabilities. And then this is the actual outcome for the classes. All right, so we've collated our out-of-sample predictions. And then the way stacking works is we would create basically a secondary model that tries to predict the outcome data based on all the predictions from the individual models. And so it turns out that when these stacking methods were first looked at, and this is held up, I think, over time, that it seems like the optimal approach to doing that is basically using a linear stacking method. So like a linear combination of these constituent models to predict the outcome. And it turns out that one thing that does even better is, let's say we're using like some sort of least squares method to do that, to use like non-negative least squares. So you won't have any stacking coefficients for each model that are negative. So what we'll do is we'll take our outcome, which is a class, and we'll put it into logistic regression using the lasso and constrain the lasso to be non-negative parameter estimates. And then what we can do is we can optimize the lasso model so it has good performance with the fewest number of constituent models. And so the result of that is the lasso coefficients for the parameters would be like the blending coefficients. So the lasso will potentially eliminate predictors from the model by giving them an actual value of 0 for their regression coefficients. So in the course of fitting the stacking model, when you blend these predictions together, some of them might have 0 coefficients and are excluded from the ensemble. And then you can look at the coefficients to see how much each is blended together, like which has the most influence on the stack. So basically that's a stacking model. We're just going to fit a regularized logistic regression, and then the outcome is the actual training set outcome, and the predictors are the class probabilities produced by all the submodels in the ensemble. It's very simple. Blend predictions is the name of the function. You give it the data stack, and then you have the option to set the different levels of regularization that are used and so on, but it basically optimizes that model. And in this particular case, it came up with a lasso penalty of 0.1, which is a fairly strong amount of regularization. And of the 322 possible coefficients you could have had in the ensemble, it actually only used 9. And then it prints out what those 9 were, for example. And then you can see across all the different models, the only models that are actually used in the ensemble is random forest shows up twice with pretty strong coefficients. The flexible discriminant analysis model is used once in the ensemble. And then a bunch of submodels for the C5 boosting of rules are used. So the 9 coefficients, most of them are C5, but I think random forest has the strongest blending coefficients. And so basically this is our stacking weighting of how these particular models are used. And so you don't see like, you don't see case nearest neighbors and other models that were used, they're eliminated from the ensemble. Now, one thing that we do here is we actually save the prediction function when you want to make the ensemble predictions as an expression. that we can just use in a dplyr mutate. And the reason for that is you don't have to have all the other model results around to make these predictions as you would if you just use glibnet or something directly. So it's a little more efficient and self-contained by doing the prediction equation this way. All right, so far we've defined our ensemble. We know which models are part of the ensemble and their relative weights, but we don't have their individual model fits for the entire training set. So far, all we've used is the resampled data set fits that we generated in the course of model tuning. And that's what this little note is here. It says you haven't actually fit the members of the ensemble yet, so do that with a function called fit members. And that's what we'll do next. There's some diagnostic plots you can get off the blending object. The autoplot method by default generates some resampling statistics. So you can see across values of the lasso penalty. On average, lower penalties had, on average about 13.5 members in the ensemble, and that drops down to around 9-ish, 8 or 9-ish, and that corresponds to when performance increases. There's another type method for autoplot that gives you the relative weights of all the ensemble members. That's a nice little graphic for you. All right, so the last stage is to actually fit the ensembles, the constituents of the ensemble model. And so fit members, which we showed before, when you run that, it will do 9 more model fits of all the submodels that it needs for the ensemble, and it fits those on the entire training set. And then once you're done with that, you're able to make predictions. So if you wanted to predict the test set for these data, you would just give it the ensemble model, and it generates the actual ensemble class probabilities using that expression that I showed you earlier. Lastly, one thing you can do is if you want to get the individual predictions from the constituents of the ensemble, there's an option called members. And if you set that to true, you get, for example, the ensemble predictions plus all the predictions from the constituent models that made up that ensemble. And that is all.
Great, thanks, Max. Yeah, so we have plenty of time for questions. The first one that came through was Amrit Singh, who asked, can the models or CV folds be parallelized to run faster?
Yes. So much like Caret, when you fit these with tidymodels, as long as we use for each like Caret does, so if you set up a for each parallel backend, all these models can be run in parallel. Not only that, but when you do the blending model in the ensemble, if you have a parallel backend registered, parallel processing would be used to optimize that also. Yeah, they're fairly computationally efficient. We took all the tricks that we had from Caret and re-implemented them in tidymodels. So it's probably as efficient as it's going to get.
Great. So the second question is from June Lee. In stacking ensemble process, can you incorporate Bayesian optimization in tidymodels framework rather than the grid search for the parameter tuning, such as using MLR MBO?
Yeah, so the tidymodels package tune has a Bayesian optimization. You could just as well give those to add candidates here. We also have some like racing methods and like simulated annealing optimization of models. We'll have this set up to any grid or sequential optimization tools that we have can feed into this. Yeah.
Right. And another one from, there's code in this question. So from Raul Torres asked, could you clarify the distinction between blend_predictions and the model obtained from fit_members?
Yeah, that's a good question. So what blend prediction does is it takes the resampled versions of these models. So for example, like the one nearest neighbor model, if we did 10-fold cross-validation, we would use the 10 different one nearest neighbor models that are fit on 90% of the training set, a separate 90% of the training set. And those are used to actually estimate the blending coefficients. So what blend prediction does is it takes the resampled results, the resampled models, and uses their out of sample values to estimate what the coefficients for blending should be. Now, once you have those, you don't actually have the models that you'll need to make full predictions, because what you'd like to do is you'd like to take, for example, this particular C5 model, fit it on the entire training set, and that will be used to generate the class probabilities that are blended, let's say, with this coefficient. So the difference between blend predictions and fit members is blend predictions tells you what should be in the ensemble and with what weights. And then fit members goes back and refits just those models using the entire training set, which is what would be needed for prediction. So that's the main difference. Yep.
Great, thanks. Yeah, and I'll forward the rest of the questions to you.
Awesome. Thanks a lot.
All right, thanks a lot.